So first I need to apologize for typesetting this in OpenOffice. I know that the text looks like a ransom note, but that's what happens when you don't use LaTeX. I'd also like to give a shout out to Colin Mulliner if he's here, and our dinosaur rock band. We're a Christian rock band. We're called Jesus Lives in the ISS, and so what we do is, we know that he's always watching us, but we think that it's easier for him to hear our prayers when he's, in an orbit that passes over us. So we need to use orbital tracking to know when to pray. As I'm sure you can guess, I'm not recognized as a legal minority religion in Germany. I'd also like to thank SkyT and Fabienne Serrer and Adam Laurie and Jim Giovetti for some prior satellite tracking work, and the Scooby crew at Dartmouth College for all sorts of fun whenever I bounce out there. This is the mission patch of the Southern Appalachian Space Agency. This was drawn by Scott Bybin, and there are a few pieces of my people's native culture that I need to point out here. On the right, the little dinosaur type thing with his finger going out, you might call him E.T., but we call these things boogers. They're like this tall and they're green, and that's why the man on the left has a shotgun. Because he doesn't want to be abducted, you see. And we've got the satellite dish in the middle, and it's sitting on cinder blocks, because that's also a piece of my people's native culture. There's a moonshine still in the background. That's kind of like vodka, but you make it at home and from corn. And then there's the mountain. It looks like there are snow peaks on those mountaintops, but our mountains aren't tall enough to have snow. These are actually that we've blown off the lids of the mountains for coal mining, which is another piece of my people's native culture. And at the top in space, you can see the International Space Station, and you can see a banana, and you can see what I think is a bolt. This just signifies space trash. I mean, there's a lot of stuff up there. And, it's symbolism that matters in these things, So, at Berlin Sides in May of 2012, I did a lecture on reverse engineering the Spot Connect. The Spot Connect is a little hockey puck type thing. This is what it looks like. And these things are great. It weighs a bit more than your cell phone, but it runs off of a couple of batteries. It connects to your phone by Bluetooth. And originally, these were emergency locator beacons. So if you were going hiking, have any of you seen the movie where the guy has to cut off his arm with a dull knife? Well, if you're hiking and you don't want that same experience, you buy one of these things, and then there's an emergency button you can push that transmits your GPS coordinates by satellite to rescue workers. But that was boring, so they had to add social media. So in addition to keeping you from chewing off your own arm, this device will also allow you to tweet and to make Facebook posts. The idea is that, as you're running, here I'm crossing the Schuylkill River in Philadelphia, and the Android phone on the left is making a post. And I did an article on reverse engineering the Bluetooth side of these things, because I use a weird brand of phone that Microsoft killed off, and I'm terribly bitter about it. But I also figured out the physical layer, and that's what this diagram shows. This transmits at 1.125 gigahertz, sorry, 1.6125 gigahertz. And it sends a pseudo-random stream. So each one of these zeros is a long chunk where it's bouncing back and forth between two different frequencies. And the same for the ones. But the way that the pattern works is that it switches the signal whenever it's going from the 0 signal to the 1 signal. And internally, there are these little pops that you can actually identify on a software-defined radio recording. And this is how you can reverse engineer the signal that the Spot Connect is sending up to its satellite network. Everything is clear text on this, and it's completely unencrypted. It just has your serial number, your GPS coordinates, and a bit of ASCII text. So if you listen on this frequency and you have the correct recording software, you can actually watch all of the Spot Connect messages that are transmitting up from your location. And this would be great, except that this is designed for hiking in areas where there's no cell phone service. So having an antenna on the uplink frequency is kind of useless. You know, you would actually have to go out to a national park, find some guy who's about to chew his arm off, and then you could listen to his uplink where he's like tweeting, hey, I'm going to chew my arm off, you know. So that's great as a proof of concept, but it's not really anything practical. So the current state of that was that I knew the protocol and I could sniff the uplinks, but I wanted to sniff the downlinks. So it's easy for me to get the thing that goes up to the satellite, but what I wanted was what comes down from the satellite. And that requires a satellite dish. But a geostationary dish isn't good enough because the satellites that run this network, there are a lot of them, it's called the Global Star Network, they fly really low across the Earth. And they fly across the Earth in very tight, very fast orbits. So they'll move from horizon to horizon in 15 to 20 minutes, which means that you either need like a sweatshop army of kids, you know, trying to aim the satellite dish as it's going across, or you need to make it computer controlled. So stepping back from the Spot Connect for a little bit and discussing some prior research, Adam Laurie did some work with a geostationary satellites. These are the satellites that stay in one position in the sky. He gave 2 sets of talks, one in 2008 and the second in 2010. And he used a DVB-S card connected to a satellite dish with a Dissect-C motor so that he could move a satellite dish left and right in order to scan a region of the horizon. His tool is publicly available. It's called SatMap. You can grab it at this URL. And then after he finds a signal, he has a feed scanner. Normally, when you use satellite TV, your provider gives you a listing of the frequencies, and your provider gives you an exact orbital position to aim your satellite dish at. But Adam's tool allows you to scan to see which frequencies are in use and which protocols are in use once you've correctly aimed your dish. And he also describes a technique for moving your dish left and right while doing this in order to identify where the satellites are. This recording here is from a re-implementation that I made of Adam's work in order to catch up with it. And you can, in this diagram, the x-axis, like as you move left and right, that shows the azimuth. That shows how far left or right my satellite dish has moved. And then the y-axis shows the frequency, and all of these dots are strong signals. So every vertical bar in which you see chunks of frequencies, well, that's a satellite. But these stay in the same position. So it's easy for me to repeat this experiment. It's easy for me to rerun it and to find the same satellites in the same position. It's easy to debug this. But it can't move in elevation. So this diagram is actually a very small slice of the sky. We're looking at a single line, maybe 10 degrees across. Maybe only 5 degrees across. So hacking KU band, the television satellites, has the advantage that you can use cheap standardized hardware. I bought one of these DVB-S cards in Mauer Park in Berlin for €3. You can use standardized Dissect motors. You can buy them at a satellite TV shop. TV signals come with video feeds, so you can actually see pictures. There was a scandal about 4 or 5 years ago where they were finding drone feeds that were being bounced across these satellites. In the 90s, it was very popular to listen to the sort of unedited sections of interviews when people would be interviewed over a satellite before Skype and such things became options. And there are also networking signals here using TCP/IP packets. So you can actually turn your DVB-S card into promiscuous Ethernet adapter and start sniffing all of the traffic that comes across. This is also a great way to get free downlink bandwidth, because you can just flood packets at an address that you know will be routed to you, or several addresses, and then you sniff it out as the legitimate receiver ignores it. But it also has some disadvantages. It only works for geostationary satellites. If the satellite does not stay in the same position relative to the ground, then you can't track it. Your dish also moves very slowly, and it only moves left and right. It won't move up and down. And you're limited to standardized signals. So while it's great that you get video in TCP/IP, you're never going to get anything weird. You're not going to get any mobile data. You're not going to get any Brazilian truck drivers. We'll get to those in a bit. I misspoke. You actually will get Brazilian truck drivers in this. So I bought a satellite dish. One of the best things about living in America is that you can buy industrial hardware cheap as dirt on eBay. I know things aren't like they used to be and you can't buy human children anymore, but this satellite dish here on the left, the one in the radome, that's my dish. And to the right, that's the boat that it came from. So this came from a military ship, but the dish itself is also available for civilian use on very large yachts. The dish itself is a Felcom 81, and it was intended for use with a network called Inmarsat. Inmarsat allows for telephone connections, and also data connections when you're on a boat. So if the crew wants to call home or wants to go to AOL keywords or whatever was popular back when this was common, they could do that. And the dish was designed to sit at the very top of a ship's mast. The reason why is that at the top of the mast there aren't any obstructions. It has a clear view of the sky in all directions. But there's a complication with being at the top of the mast, which is that the ship is rocking beneath you and you're moving more than the rest of the ship. So they have stepper motors for azimuth, elevation, and tilt, and then they have spinning gyroscopes. Back before the iPhone, there was this dark, dark time when gyroscopes actually spun. And this is the sort of gyroscope that it has. It actually has 4 of them so that it can measure its movement. And then it has a control computer. So the idea is that the dish itself can be moved while remaining absolutely stable with regard to the gyroscopes. So it compensates for the rocking of the ship beneath it as it's targeting a stationary satellite. And in America, this costs $250, but it's electronics equipment. So while you think that would only be 180 euro, it's more like 2,500. And that's before import duties and it being impounded. We also have this lovely culture in which people love excuses to use their trucks. So the guy that I bought this from offered to deliver it to my home for only $200. It was an 11-hour drive. But if you wanted this, you'd have to bring it back in your carry-on luggage, and that could be awkward. Now, so I got this dish, and I decided I had to do something with it. So I created the Southern Appalachian Space Agency. I'm from the state of Tennessee, formerly known as the state of Franklin until North Carolina invaded us. And it's OK. I know Europeans suck at history. Now I'm trying to think of how to show you on a map where Tennessee is without having a map. But, you know, it's OK. I know you suck at geography and would forget it soon. Texas is our first colony, but it's actually a decent drive to the east. Due east. You don't actually have to go. Anyways. So what I did was I took these motors, which were designed to be able to move the satellite dish to compensate for the rocking of a ship, and I repurposed them to track through the sky while the ground is stable. We don't have very many earthquakes in Tennessee. The last one that we had made rivers run the wrong direction. But it's okay, you know, it's a geography thing. So, so this allows me to track things that are moving through the sky, but it doesn't actually matter where they're moving in the sky because that's just a software problem. So in addition to tracking objects that are in low Earth orbit, by a software patch, I can also track things that are in deep space. It's not much harder to track deep space probes or stars than it is to track items in low Earth orbit. And then I added a software-defined radio, which allows me to record a signal now and then demodulate it later, which is necessary if you intend to reverse engineer a signal. Because a lot of the downlinks from these satellites are completely undocumented. And being able to tune into the right frequency is only half of it. You also need a recording of sufficient quality that you can reverse engineer it after the fact. We're sort of spoiled by software-defined radios in that when doing software-defined radio work, we usually have a very good signal to work from. So having high-quality signals for later reverse engineering is necessary. And I really wanted to be able to identify undocumented downlinks for low Earth orbit in the same way that we already do this for geostationary orbit, using tools like the ones that Adam Laurie and Jim Giovetti made. So I built a software framework as a collection of Python daemons, and these run across a home area network in my house. There's a BeagleBone inside of the radome, and an x86 server in the house, or AMD 64, or whatever the kids call it these days. And then I used Postgres for coordination, so that all of these daemons can talk to each other without me really caring which machine they're on. So for maintenance, I can have my laptop pretend to be the dish, and I can have stepper motors on my desk, and I can watch them spin, and I could even make a model of the dish and swap these components in and out without the rest of the network being confused. This also allows for SQL injection attacks to physically move my dish, which is why the SASA network is not on one of those fancy Web 2.0 things. Because if you could inject, say, update target set name equals Voyager 1, then my dish would physically move and start tracking Voyager 1 through the sky. Voyager 2 doesn't actually come into the sky because of my position in the northern hemisphere. So it's okay, I know you suck at geography, but Voyager 1's going up and Voyager 2's going down. There's a Realtek software-defined radio for the radio reception, although these things are garbage, so I'm in the process of replacing this with a HackRF. There's also an iBot board for motor control. We'll get back to that in a minute. And there's an inertial measurement unit from VectorNav, which actually measures using the fancy MEMS gyroscopes and a MEMS compass how I'm moving. This isn't accurate enough to target the dish, so I'm still counting steps to move the dish. But it is accurate enough to tell me when my belts have broken or when I'm up against a physical obstruction. This is SkyT helping me out with the dish. He's zip tying it, because we know everything about duct tape where I come from, but we don't know anything about zip ties. So we had to bring in a German engineer, and we call him a jerry-rigger, but this is the satellite dish itself, and you can sort of see in this photograph where we've strapped on the equipment. There's like an umbilical cord, or more like a spinal column that actually runs up the back of the dish. So we just added new cables onto that line and then zip tied them in place. And SkyT came up with all these crazy ideas like that we should use chains and zip ties to make sure that the cables don't tear themselves out. And that worked tremendously well in practice. So as this thing spins around, by the original design, there's a ring connector that all of the signals go through, that all of the networking goes through, that all of the rest goes through. And that worked in the 90s because it had no reason to send anything faster than 9600 baud. But with the modern signals going across it, I need 100 megabit or even gigabit Ethernet. That's not enough. I need more than 2 wires. So there's a cable that comes across it, and then I rely on software to keep it from wrapping that cable around itself. So it can only move, say, 400 degrees around, but that's still more than a full circle. So by stopping halfway and moving back, I can prevent it from getting snagged. We've got the beagle bone on the left. In the middle, there's a USB hub, and on the right is the motor controller. The beagle bone runs Debian Linux and takes care of sending the software-defined radio recordings over the network. It also takes care of updating the motor positions to be the ones that the database declares should be current. The stepper motors themselves are the originals that the dish was designed with. And they're running to an iBot board. The iBot board was intended for plotting on Easter eggs. I mean, I feel, isn't that neat? So you can actually aim a satellite dish that's as tall as you are with all of these fancy motors using less sophisticated equipment than what's used in a 3D printer. Don't panic, though. It's a hell of a lot more reliable than a 3D printer. But we needed some sort of backup, in addition to the inertial measurement unit telling us when the device has snagged itself. It would also help to have a visual cue, because the satellite dish sits in Tennessee, and while I love my hometown, and I'm very proud of being Tennessean, it's also a long way to travel when you need to reorient a dish. Using an accelerometer, it's easy enough to correct the elevation, because you can use the accelerometer as a level, and you can use that to tell how high up the dish is pointing as an absolute scale. But the compass isn't very accurate. So instead, as a backup, we have a webcam that's taped to the top. Taping is my people's native culture. We have it taped to the top, and then it's pointing backwards. So this gives us like a rear view camera from the dish's position. So as the dish sits inside of its radome, junk cars in the yard are also my people's native tradition. So, the dish sits there next to my brother's Toyota Supra, and that thing, that thing flies as soon as it gets an engine put back in it. So the dish sits there, and it's moving, but externally you can't see where it is, which means that I can't call my family in Tennessee and blackmail them into yet again looking at my dish to tell where it's pointed. There are bolts that hold this down. It takes half an hour to remove the lid, another half hour to put it back on. So instead, we took the radome. That's Frank. He's my cat. Give a cheers for Frank. Yeah, we had such a great time with Frank, and we never knew that she was pregnant. If you happen to need kittens and want to pay the customs fees, I'll hook you up. So then we took tape and ran tape down the edges of the radome, and then marked it. So from the markings, you can tell which clock position the back of the satellite dish is pointing at. So if you point the dish toward 12 o'clock, you know that you're roughly at 6 o'clock, so you know that it's pointing south. And then you can sort of scan the sky for a stationary target and navigate off of that to recover your position. Software-wise, now remember, the whole thing runs through Postgres. So I just tunneled Postgres over SSH, and then I wrote a Python client that displays the satellite positions and the satellite state in Pygame. This is intended for making those games where you see the rabbit and the rabbit jumps on the other rabbit. But it works, and it works perfectly well enough to target the dish, because all that this software has to do is plot the positions of the satellites and give orders back to the database when I click on a satellite or click on a position. It can also display stars. So the red items are satellites which are not selected. The green item is GOES 3, which is the satellite that I'm targeting. And then the white items are stars in the sky. Now this is a plot in which the azimuth is on the x-axis and the elevation is on the y-axis. But I can also arrange it into a polar plot, which sort of gives me an upside-down view of the satellite dish looking at the sky. And I doubt you can read it, but just above the green circle in the center, that's Polaris, which is the North Star. It's also weird because, working on this, I thought that I got really good at astronomy until I realized that I only knew what the stars looked like during the day. And it being Pygame, you can actually run it on a mobile device. So the same client that runs on my laptop can also run on my Nokia N900. A significant portion of the GUI client for this was written while stuck on the U-Bahn, connected over 3G, SSH through, and just using Emacs on the phone. If you're one of those people who needs to complain about the N900 being too old, it also runs on the N9. And then you can take the data out of this and you can run it through scientific software. In addition to the software-defined radio recordings themselves being dumped out to like a text file or a binary file on disk, you can also dump out things like the received signal strength indicators. So this is a screenshot in which I'm identifying different satellites that I've seen in the sky based upon their downlink signal peaks. You can see the noise floor there at the bottom, and then there's a rather strong signal on the left and a weaker, narrower signal on the right. Now, the daemons that build this up, you need an orbit prediction daemon, because you need to know where the satellites are and where they're going and where they will be by the time you get to them. You need to update the orbits themselves. Low Earth orbit satellites are described in TLE files. These are called two-line entry. And they're called two-line entry because they're 3 lines long. These were originally used by NORAD for intercontinental ballistic missile tracking. Because a ballistic missile is basically in orbit, it's just that that orbit happens to collide with the Earth. But this format isn't terribly accurate for satellites that adjust their own orbit. So anything that has fuel or has engines or changes mass will vary its position. And this also doesn't account for drag. So because the missile itself, it goes up, it goes down. It's not orbiting enough for the light drag in the upper atmosphere to matter. But for a satellite, it does. So these two-line entries will work for a matter of days or maybe a couple of weeks, but they don't last longer than that. So you need a daemon that grabs the new files from SpaceTrack. And this is just a matter of like a recursive wget and then parsing the files. But it still needs to be done. You also need motor control, because you need to move the dish physically to track your target. You need input from the inertial measurement unit. This comes over a low-voltage serial port. And then you need radio daemons to handle spectrum analysis or downlink recording. And these you'll have several of, and you have to swap them out. So you'll begin by using the spectrum analyzer to identify that your aim is accurate, that you're accurately tracking the targets well enough to get a recording from them. And then after that, you begin to take software-defined recordings of them. And eventually, you might have a standalone application that parses what you're receiving, such as the Osmocom guys did with OpenGMR. So for orbit prediction, I began with a DOS program that had been ported to Unix called Predict. And this worked, but it it's garbage. It only supports 20 satellites, plus the Sun, the Moon, Venus, and Mars, but no other planets. Because it's designed for astronomy photographers who want to get a picture of something as it comes over the horizon. You know, I need to track hundreds of targets and then write a script to opportunistically pick the ones that I want to record. Because otherwise, you have to like, set an alarm clock for the half-hour pass in which you can play with something. This software does allow you to query the results by UDP, though. So you can just send it a flood of request packets, and then it will flood back with the data you're looking for. So I switched to a library called PyFM, which allows you to track hundreds of birds. It has no UDP nonsense. It will also calculate satellites, planets, and stars. And the really nifty thing about this is that you tell it, you know, it being a library, you tell it when to update the individual object that you're interested in. So you can update objects that are out of view or uninteresting more slowly than the ones that you care about. So I managed to track every single item in geostationary orbit. This thick ring here is the Clark belt of all satellites in geostationary orbit as viewed from my southern horizon. The two-line entry files you can get freely from cellistrack.com. So there's just a simple script that grabs them and then inserts them. And the prediction daemon will actually select them as it's loading up. Because all inter-process communication is running through this Postgres database. And this daemon can be moved to a different machine if I needed more computing power or anything like that. The motor control daemon, well, the iBot board is designed to take stepper motor commands. It shows up as a USB serial device on Linux. So as I plug it into the BeagleBone, it appears as /dev/tty ACM0. And the baud rate doesn't matter because this is a USB device. You then send it simple commands, like SM 3500 -400 means that I want to move a stepper motor for 3,000 milliseconds. I want the first motor to move 500 forward, that's up, and the second one to move 400 left, which is backward 400 steps. And then it will count that out, and then it sends me back an OK. If I want to disable the motors, I send EM00. This allows the motors to be freely spun, because normally a stepper motor will physically hold its position. You need to turn them off in order to slide the dish around. EM11 will enable both motors in 1/16 of a step mode. The stepper motors can do fractional steps because they're holding themselves in position. So you can see the motors themselves with the belts and the gear train. This thing on the right would probably be illegal for me to turn on. The thing on the right is a 250-watt amplifier. The stepper motors themselves just have 6 wires. In a lot of 3D printer type stuff, they ignore the middle 2. So you just chop off the middle 2 wires, you run the other 4 to your stepper controller, and you're good to go. The belts and stuff need to be measured in order to figure out exactly what the gear reduction is, because you need to know how many steps form a degree. The inertial measurement unit, this Vector Nav 100, it's a MEMS gyroscope, an accelerometer, and a compass in a single box. It costs $500, which was more than all of the other equipment put together. Now, the compass is confused by the stepper motors because the compass is measuring magnetic fields. So you need to mount this physically as far away from the stepper motor as possible. And the gyroscope is confused by motor jerk, which is a shame because stepper motors work as a series of jerks rather than as a single consistent motion. And the accelerometer is confused by gimbal lock. So you have to switch it to a quaternion mode in order to get consistent values out of it. And if I had to do this over again, I'd really try to drop this piece of garbage. But it's a lovely technology when it works. Now, for position calculations, the elevation itself comes from the inertial measurement unit, while the azimuth comes from the motor daemon. This is because the accelerometer can very accurately tell which way the Earth's gravity is pulling it, whereas the accelerometer has to integrate jerks over time in order to figure out its position. So the accelerometer will drift while the and the compass will be confused by the magnetic fields, while the elevation is just a single accelerometer that doesn't drift. And the IMU will become a backup for these things in order to figure out how to make it reliable. But at the moment, the position measurement is infinitely more reliable. And the tilt motor, I'm not using at present, because on a ship that's rocking, it's necessary to tilt the dish. On a satellite dish that's staying still, the only use for tilting the dish is so that you can follow the arc of a satellite through the sky by only moving a single motor. Photographers do this when they're trying to get long exposures of moving satellites. At the moment, my software doesn't support this feature, but if it turns out to be necessary to get higher quality recordings, I might add it. There are radio daemons. The first is a spectrum analyzer. This just measures the signal strength on each frequency, and it does it by the power spectral density function. Cool. And the strength itself will vary with the position error. So this allows you to figure out how far off you are by sort of testing by overshooting just a little bit or undershooting just a little bit to center on your target. The downlink recorder dumps the I and Q values in the software-defined radio directly to an NFS share, which can later be decoded and read and reverse engineered. I've got a whole table of the spectrum data, and then I plot that in a tool called Viewpoints, which NASA releases for dealing with giant scatter plots in multiple dimensions. Each view takes 2 dimensions, and it's tons of fun. Client GUI uses Pygame. I have Postgres for communications, and the server does all of the heavy lifting, so the BeagleBone itself never has to do anything complicated with regards to the software-defined radio. This is also a mode. These faint blue lines are positions at which I've seen particularly strong signals in order to identify which satellites are active and which ones are inactive, because satellites die over time. And particularly useful targets for reverse engineering are satellites that are out of commission or outdated. I'm running out of time by these markers. Does that mean that we're skipping questions, or does that mean that I need to be off the stage? Not having Q&A, OK. So today I get accurate tracking of satellites. And this thing can run unattended 24 hours a day for months without maintenance. Like I said, it's nothing like a 3D printer. It takes software-defined radio recordings. It can provide maps of views of different satellites to the sky. The next step is I want to publish a port scan of the entire sky. So which frequencies are in use on which birds for every bird that ever comes above Tennessee on every downlink that fits my antenna, as well as a database of software-defined radio recordings. If anyone would care to donate a truckload of disks, that might be handy. I'd also like to make other ground stations. The software that I've written ought to be portable to new hardware, so there's nothing that should keep you from being able to port this to run on your own dish. And I have a large yard, so I could conceivably have a dozen of these things. Another way that you can do it, and the way that it's traditionally done for, say, cube satellites, is having Yagis or other loosely directional antennas in order to receive the signals. I went with a dish because I wanted more selectivity. I wanted to be able to get reverse engineerable recordings rather than intentional ones for which I already knew the downlink protocol. So this is my van. My van is amazing. Thanks to Nick Farr. I had a bit too much to drink in Montreal, and I called Nick Farr and I said, Nick, I want a duck. A DUKW, like those amphibious troop transport vehicles. And Nick said, sorry, I can't get you one, but do you want a news van? And I said, hell yeah, I want a news van. So this pole in the background, that's not a lighting pole. That's actually part of the van. This is the antenna retracted. This mast goes up 20 meters by pneumatic power. There's an air compressor on the back. Here's the control panel. There's an air-conditioned office in the middle. This has 4 19-inch server racks, as well as some AV equipment that was left over. I was particularly excited about the video monitor, which supports PAL, which you folks are familiar with, NTSC, or Never the Same Color, which is my people's native culture. But most importantly, it does SACAM, system essentially contrary to the American method. So in addition to my radio equipment, I'm adding my Soviet PDP-11, which was... and that's not a joke. I have a Soviet PDP-11 thanks to the kind folks at the Positive Hacking Days conference. This is the control panel. And that's my talk.
Thank you so much. There actually is time for Q&A now.
Well, first I'd like to introduce you to my cat. If we could go back to the prior image. This is Frank. We didn't know it at the time, but Frank was knocked up when this picture was taken. If you'd like kittens, get in touch.
Okay.
Are there any questions?
Great talk. What's the most interesting signal you've decoded so far?
At the moment, I'm sort of stuck at the L-band range because of filters that I have yet to remove. So everything gets attenuated and becomes annoyingly quiet outside of the 1.5 to 1.6-ish range. The global star network is what I'm most interested in targeting next. I can't wait to see what people are tweeting while they should be enjoying nature.
There's a question from the internet.
Yeah, the internet has many questions. So first one was, is there really no authentication or encryption on the Q-band IP services, so you can just spoof at will? And can the birds see the physical location of the source accurately enough to find who is spoofing?
I'm not an expert in KU band. For the downlink, the bird has no clue as to the location of the dish because you're only listening. They can roughly figure out your geographic area because they need to figure out where the spot beam is going. So they might know whether you're in, say, Germany or in France, but they won't know whether you're in Heidelberg or Mannheim. They do have forms of authentication for many satellite networks. Satellite TV is one of the best protected network services because of the satellite wars in the 90s, in which TV pirates would fight back and forth with smart card designers. But there are also many unencrypted links, and because of standard protocols, those are particularly easy to find in KU band.
You've been talking about using RTL SDR from Osmocom, and you were talking about your spectrum analysis program. Is this one working with RTL SDR?
So RTL SDR, so I'm using the RTL SDR, not the Osmo SDR, which are separate. The spectrum analyzer is working with the RTL SDR. My complaint about the RTL SDR is that when you have a strong signal next to a weak signal, the weak signal is utterly useless for interpretation.
Okay. Thank you.
Another question from the internet?
Okay. Next question from the internet is: how do you record the radio signal from the dish? At what sampling rate?
The RTL SDR samples at 2 million samples per second. As soon as I switch it over to the HackRF, I'll be having 20 million samples per second. The sampling rate can be reduced once the bandwidth of the signal is known for reduced storage. And the recordings can also be compressed. But it's still a hell of a lot of storage.
Any other questions?
The internet has more questions.
Okay.
Did you look into obtaining a capacitive high bandwidth coupler as used for the rotary gantries in CT scanners? Those can apparently transmit contactless several gigabytes per second bidirectionally.
I've not looked into those. It seemed better to have an umbilical cable and to be careful not to snap it. The whole thing was done for a budget of less than $2,000 and could be recreated for less than a budget of $1,000. And so we tried to avoid fancy parts. The local Radio Shack loved us because we'd swing in and buy all sorts of crazy stuff. And as soon as we told them that we wanted the satellite dish to dance Gangnam Style, cool. Thank you kindly.